Hello students, welcome to the class. So today's class is going to be very important from the chapter point of view. So today's top section would be 4.3 and this is the third lecture series of the chapter chemical bonding and molecular structure. So this is the disclaimer. In this class our objective would be to see the bond parameters. Now there are multiple bond parameters that are used to quantify a given chemical species to the molecular structure. So we will go through those parameters and try to understand that what is the definition, specific definition of those parameters and how they are used to predict the specificity of a molecule. So it is from the section 4.3 bond parameter, in which we will see bond length, bond angle, bond enthalpy, bond order and resonance structure. So this is a bonus part of the lecture. So it is different from the bond parameter, but the most important one. And the last is polarity of bond. So there are total of 4 bond parameters and 2 important properties. So we shall begin the lecture now. First of all, we will deal with what is bond length. If I give you a very simple definition of bond length, then it is the distance between the nuclei of 2 bonded atoms in a molecule. Remember, you have to consider the distance in case of bonded state. How? So, consider a molecule which is made up of 2 atoms A and B. Now, they are chemically bonded to each other and there are 2 distances which are being mentioned here, RA and RB. So RA is the distance from the center of A to the periphery of the A. Similarly, RB is the distance between the center of B to the periphery of B. So what can you tell about the bond length? It is the summation of this contribution from RA and RB. So if I tell you that your whole bond length can be considered as a contribution from A and B, then that would be true. So this can be written as contribution from A, which is written as RA, and contribution from B, which is written as RB. Now these two terms RA and RB are very important, and you have already seen this term in the previous discussion of classification of element. So I would suggest you to think about that what was the term which used in the case of RA and RB? Sorry. So the term was covalent radius. Now why I am telling it covalent radius? Because here you are not talking about the actual atomic radius, but yes, we use covalent radius for the non-metal. So that would also be an appropriate term, atomic radii, in case of non-metal. So you should think of it in a way that you are thinking atomic radii for the non-metal. Now the definition is also very simple. We have already seen the definition. Again, I will try to explain it in a much simpler way. It is the radius of an atom's core in which it is contact with the another adjacent atom, and that too in the bonded situation. So this is the diagram. Remember students, you can't calculate the RA and RB if your A and B molecules are attached. But to calculate that RA and RB separately, you have to consider their individual molecules. Again, I am repeating it. So the previous part we discussed, there we saw RA and RB. But we cannot calculate RA and RB from the distance between A and B. That is not possible at all. We have to consider the individual molecule where only A is present, and that is the case here, A2, or the B is present, which can be B2. Suppose we are calculating the radius RA. How we will calculate? We will take a molecule A2 in which A and A are identical and they are bonded, and dA is the distance between their core. Then how will we calculate the covalent radius? It will be simply half of the distance between two similar atoms. Remember, you can only take the half distance when the distance is between two similar atoms, as is the case here, A and A. Now, if I ask you how you will write this whole thing in a line, then that would be very simple. Covalent radius is equals to the distance between the two A's divided by 2, which is equals to the RA. Yes, that is true. So whenever you are calculating the radius in terms of covalent part, then some part is superimposing, or you can say that they are overlapping with each other. But we don't have to worry about that part. We just here to explain this simple thing, that if you want to calculate the radius of A, you will take a molecule of A, calculate the distance between their cores and divide it by 2. As simple as it. And the second most important point, you cannot calculate the radius of A from the distance between A and B if A and B are covalently bonded to each other. So we saw that in the previous class, in the previous slides. Okay, I guess this part is clear to you. Now we will take a second type of radius and a much more important type, which is known as van der Waals radius. Now we have talked about this van der Waals radius, right? When we were discussing the classification of elements, we said that noble gas cannot be present in the bonded state. Yes. So in that case, we have to take the van der Waals radius. How? So if I want to define the van der Waals radius, it is basically the size of the atom, and this size also includes the valence shell in the non-bonded situation. So let us take a diagram to understand that. So these are two molecules of chlorine. This is first molecule chlorine and this is the second molecule of chlorine. How do I calculate the van der Waals radius? It is the shortest possible distance between two atoms which are not bonded to each other. You can see here that this is a separate chlorine molecule and this one is a separate one, and they are not bonded to each other. Then we will calculate the least possible distance between two adjacent chlorine atoms which are not bonded. Okay, so this will be calculated as, so in chlorine case it comes out to be 360 picometer. Got it? So what we can write? What will be the van der Waals radius? If 360 picometer is the distance between these two isolated atoms, which are not I would say isolated, bonded atoms, but not bonded to each other, that will be half of the distance of this 360 picometer. It will be equals to 180 picometer. Now you can also calculate the covalent radius, because here in the diagram we have the value of the distance between the two chlorine atoms which are bonded to each other. Now you can clearly judge the difference, the minute difference between van der Waals radius and covalent radius. So in case of covalent radius, we are considering the distance within a molecule, and in case of covalent radius, we are considering the distance between two different molecules. Got it? So if you consider it between two atoms of the same molecule, it is given here as 198 picometer. Then how you will calculate the covalent radius? We have seen the formula. It's very simple. We will simply divide this 198 picometer by 2. Is it clear? So if we do it, we will get the covalent radius as 198 by 2, which is 99 picometer. So two things are noteworthy in this part. Again, I am repeating it. It's very important. Whenever you calculate the covalent radius, you take two atoms which are bonded to each other, and here is that case. Whereas in the second case, which is van der Waals radius, you take two atoms which are not bonded to each other, and you take the minimum distance that is possible between them. Got it? Now, moving on further. So this is about the bond length. So we have covered the bond length part. We know the definition now. Now we will move to the next parameter, which is bond angle. What is bond angle? A very simple definition is given here, but an important term is mentioned, that it is the angle between the orbitals of bonding electron pairs around the central atom in a molecule or complex ion. So let us try to understand this with the help of a H2O molecule. So what is being written here? It is the angle between the orbitals containing bonding electron pairs. So this is the bonding electron pair. Okay. And here is the second bonding electron pair. Now the angle between these two and around your central atom. So this should be always in your mind, that you will always take the central atom while calculating or while judging the bond angle. In case of water, this angle comes out to be 104.5 degrees. Now the important discussion would be here is that you should always remember that you will be calculating the bond angle in case of your central atom. Okay, you will not consider it for the surrounding atoms. Then here is your next bond parameter, which is known as bond enthalpy. What is bond enthalpy? It is the energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. For example, if we consider a H2 molecule, then we are to break this encircled bond. So this is a H2 molecule where there is a bond in between and it is encircled. So this is being broken and we are getting two isolated gaseous atoms. You can see here, in this process, we are breaking 1 mole of bond. So if I ask you how many bonds are there in one H2 molecule, what would be your answer? What is the number of bond in one H2 molecule? If you know that answer, then you will be also able to say that what is the number of bond in 1 mole of H2 molecule. Again, I am repeating it. Number of bond in one H2 molecule. There are not two bonds. There is a single bond between one H2 molecule, I guess. Okay. There is a single bond between one H2 molecule. You just draw a hydrogen and hydrogen. You will see it clearly that one bond is between hydrogen and hydrogen. Right? If I am saying that I have to break 1 mole of bonds, then how many bonds should I break? I should break 6.022 into 10 to the power 23 bonds, because here we are talking about 1 mole of bonds. Got it? So the overall point is that bond enthalpy is the amount of energy which is required to break 1 mole of bond. If you are considering it for the hydrogen molecule, then between two hydrogen atoms, we have one bond. Therefore, for 1 mole of hydrogen molecule, we will have 6.022 into 10 to the power 23 bonds. And the energy that is required to break this bond is 435.8 kilojoule per mole. Now, here is a question for you. Try to draw the Lewis structure of N2 nitrogen and calculate that what number of nitrogen-nitrogen bonds are possible for 1 mole of nitrogen. Okay, I am again repeating it. Try to consider a nitrogen molecule and tell me that how many bonds you should break between nitrogen and nitrogen to break 1 mole of nitrogen into gaseous species. Okay, so I am moving further. Meanwhile, in this case, remember the unit will be kilojoule per mole, because we are considering the energy that is required for per mole. Yes, the correct answer for N2 will be 3 into 6.022 into 10 to the power 23, because one nitrogen molecule has 3 bonds between the 2 nitrogen atoms. Okay. So for 1 mole of nitrogen, we will require 6.022 into 10 to the power 23 multiplied by 3. That is 18.066 into 10 to the power 23 bonds. I hope this is clear to you. Now, a peculiar representation is been given here. If you see here, then the enthalpy change is being represented by delta AH. So, why I am telling it delta AH? If it is bond enthalpy, so there must be a similar subscript in the down instead of this A, because this A is representing your enthalpy of atomization, and enthalpy of atomization is equals to the bond enthalpy. Got it? Now what is enthalpy of atomization? To convert 1 mole of this hydrogen into its constituent atom. Atomization means conversion of molecule into atom. So you can say here in this case that bond enthalpy is equals to enthalpy of atomization. Now enthalpy, you must be hearing this term multiple times, enthalpy. So enthalpy is basically the energy change. Okay, I can keep it as simple till now before we move on to the discussion of thermodynamics. So you can simply think it of a way that it is the energy change, whether the energy is released or it is being absorbed. So if I ask you that in this process, is the energy released or is it absorbed? So what would be your answer? Keeping in mind that your value of enthalpy is given in positive terms. Okay, so again I am repeating it. Is the energy absorbed or is it released in this process? It is being absorbed. Yes. Why? Because we have a positive sign against the value. I hope this bond enthalpy and bond angle are clear to you. Now, the bond enthalpy part has a little problem in it. What is that problem? That this simple method is not applicable to the polyatomic molecules where we have more than one bond of the similar type. So let us try to understand that. To solve that problem of a polyatomic molecule, we take the case of average bond enthalpy. And this average bond enthalpy is only used for polyatomic molecules. Remember that. How do we understand it? It's very simple. Take the example of a H2O molecule. So this would be the bond line structure. I would say the Lewis structure of the H2O molecule. H single bonded with O, then O is single bonded in turn with H. So this is the whole picture. If you see this picture, then you would recognize a very important point here. Apart from the hydrogen-hydrogen case where we have only one type of hydrogen bond, here we have two types of hydrogen bond. How? Let us try to understand this. How these two bonds are different if we are breaking it. Okay. If we are breaking it, then these two bonds are not equal. Suppose we are breaking the first bond, the left one. So I have encircled it, and on breaking this, we get two species, one H and one OH. Got it? So when we were breaking the first bond, we were breaking it in a H2O molecule. Okay, but we are left with now a OH molecule, and in the second case we will break the bond between O and H, and that also an isolated one. Got it? Again I am repeating it. So in the first breaking part, we are breaking the bond between OH in a H2O molecule, but if you consider the second breaking of the bond, then here you are breaking the bond between O and H, and it is a single O and H only. You don't have a H2O in total because one H has already been removed. And you can clearly see the difference also between these two. For the first one, we are giving 502 kilojoule of energy per mole of the water molecule. Whereas in this case, we are giving 427 kilojoule per mole. Means to break these two bonds, we require two types of energies. Okay, because we can't break both of this bond simultaneously. We will break it one by one, and that will give us two different values of the bond enthalpy. Now our problem is that which value should you take? Because here we are not confined to one value, as in the case of HH, where we have only one value between one bond between H and H. Here we have two bonds, right? So in this type of cases, what we do, we take the average bond enthalpy. Take the first value of the OH bond cleavage, take the second value and add both of them and divide it by 2. We are taking two values, so we are dividing it by 2. If there were 3 bonds of the similar kind, suppose in a random case, then we will divide it by 3. So this is important to understand. Since there are 2 values, you are dividing it by 2. You are simply taking the average. If you take the average of these two, you will get your average bond enthalpy as 464.5 kilojoule per mole. And in case of H2O molecule, for the bond enthalpy part, you take the average bond enthalpy only. So if someone is asking you that what is the bond enthalpy in case of H2O molecule for the OH bond, then you will tell the value as 464.5 kilojoule per mole. I guess this is clear to all of you. Now we will move further. So our next discussion would be related to the bond order. Okay. So now we will discuss about the bond order. Yes, of course, these two values will be given. If you are being asked about the average bond enthalpy, these two values will be surely given. But you will not be asked such questions in the chemical bonding chapter, hopefully. Okay. So in the exams, you get a complete test. So there you don't have to worry about it. Suppose you are giving a chapter wise test, then there you won't see questions on bond enthalpy more often, but there can be questions. I'm not telling it, I'm not ignoring it completely, but this part is mostly of the thermodynamics. But if you know it here, then it will be a great advantage for you. There you will not face difficulty to understand this all. And be assured, you will always get these values to calculate your answer. Okay. Now moving on to the next bond parameter, which is bond order. So what is bond order? It is simply the number of bond between two atoms in a Lewis structure. So you just have to count the number of bonds. Okay, you don't have to do a rocket science. You just count the number of bonds and you will get the bond order. We can take examples of it. Before taking the example, let me tell you a very important point here. If you have two isoelectronic molecules and ion, molecules or ion, they will always have the same bond order, given that they have same number of atoms. How? Suppose you are taking the case of two fluorine atoms and two oxygen atoms with a negative sign. So the complete molecule is F2, and in the second case it is O2 2 negative. Okay, so two oxygens are here with a 2 negative sign. If you draw the Lewis structure of these two species, you will get a single bond between these two. Second thing, if you calculate the number of electrons in this O2 2 minus and F2, then you will get the same number of electrons. So what would be the number of electrons for the F2 and O2 2 minus? Remember, it is same for both of them. It's very simple. The total number of electrons will be obviously the double of the electrons present in case of fluorine. So it is 9 to the 18. Okay. Similarly, for the O2 2 minus also it will be 18. And as they are isoelectronic species and they have the same number of atoms, your F2 has 2 atoms, your O2 2 minus has 2 atoms. Therefore, they will have a bond order of 1. And how we have calculated it? We have just seen the number of bonds between two Fs, and that is equals to 1. Okay, I hope this is clear to you. Now let us try to understand this with the help of another example. The next example is N2CO and NO+. Again, three species are given here. You can try to draw their Lewis structure. When you will draw it by yourself, you will see that all of these three species are what? They are isoelectronic and they have the same number of bonds between them. Why? Because they are isoelectronic, so they are having the same number of bonds. Therefore, their bond order is also same, which is equals to 3. So, how they are isoelectronic species? What are the number of electrons in each of this? How do we know it? It's very simple. Take one nitrogen valence electron and multiply it by the 2, or I would say total number of electrons and multiply it by the 2. That would be equals to 14. Okay. And same is the case for CO. Take oxygen, it is 8. For carbon, it is 6. So 6 plus 8, it is 14. Similarly, for NO+, if you take, nitrogen is having 7 electrons, oxygen is having 8 electrons, and there is a positive charge. So you remove 1 electron. Therefore, 7 plus 8 minus 1 will again give you 14. So all these three species are isoelectronic. Therefore, they will have the same bond order, which is equals to 3. Okay. Now, we will try to develop a relation between the bond order, stability and its properties. So remember students, 3 important points. As you increase the bond order, first thing happens is that your strength of the bond increases. So you have to apply more energy to break it. And it's very obvious. Second is the bond length decreases. So bond length is inversely proportional to the bond order. More is the bond order, more is the number of bonds between two atoms, shorter will be the distance between the two. That will result in lower bond order. And the third is greater is the number of bond order, stable is the molecule. So these three are very important points. What? The first one is bond strength increases with increase in bond order or increase in number of bonds. Second is bond length decreases with increase in number of bond order. And third, molecule become more stable due to a greater number of bonds between these two or any two bonded atoms. I hope this is clear to you that what is bond order. So you can try multiple Lewis structure by yourself and try to calculate the bond order for each of them. Our next discussion will be on resonance structure. So this is very, very important for you. So listen carefully about this. Now, if I talk about the simple definition, then this definition says that if a single Lewis structure cannot describe a molecule, then multiple structures are used to describe the same. What is the meaning of this? Okay, so we will try to understand this line with the help of a illustration. So basically what happens if you are taking a molecule and drawing its Lewis structure, then on the basis of that you are trying to get the bond order and all, you will see that your Lewis structure is not able to explain all of those. In that case, rather than taking one Lewis structure, we take multiple Lewis structure, and those are known as resonance structures or also known as canonical structure. So both terms are important. Remember both of these terms. So what can be the example of that? Let us take a ozone molecule. Okay, we have already seen the Lewis structure of ozone molecule. Now a question arises. Many of you would be facing difficulty in drawing the resonating structure. There is no shortcut for doing that. I would suggest you to try and draw it for multiple molecules which exhibit this resonance phenomena. Okay, take the case of CO3 2-, take the case of O3 and try to draw it by yourself. In this case, if you will see, then three structures are possible. Two are the canonical structure, which are represented as 1 and 2. And the third one, which is the most important one, it is called as the resonance hybrid. Now, what is the meaning of this resonance hybrid? It is simply signifying that you are blending these two canonical structure and giving a third structure. So you can think of this third structure as the blend of this structure 1 and 2. So again I am repeating it. What is resonant hybrid? So it is the true electronic structure, and it is the one which represents the molecule more accurately. Neither this one and nor this 2. So this the third one is the most important in representing your O3 molecule, and it is called as resonance hybrid. Now I said that one Lewis structure is not able to explain this formation of O3 molecule. Why is it so? We will try to understand this thing with the help of experimental evidences. So this is the diagram that we have seen earlier. Three things are very important here. First is, if you look here in the structure 1 and 2, then two types of bonds are possible in case of O3. What are those bonds? The first is single O bond. So you can see in the structure 1 that there is a single O bond. In the structure 2 also there is a single O bond. And it is seen that generally your single O bond has a bond length of 148 picometer. So this is not the actual bond length, but it is the general case. Okay. So if it was single, then one of these should have 148 picometer. Okay. Again I am telling it. It is found that the single O bond length is 148 picometer. So if you take the case of ozone, it has one single bond and one double bond. So at least one of these bonds should have a length of 148 picometer, because one should be single and one should be double. Similarly, if 121 picometer is the bond length for the double bond between O and O, then out of these two bonds, if first is 148 picometer, then second must be 121 picometer. So this should be the case in case of O3. But what happens in actual? In reality, it is seen that both of this bond have a bond length of 128 picometer. So this is very groundbreaking. This was very groundbreaking in those times. Okay. According to the Lewis structure, one should be single, one should be double. So one should be 148 picometer. So these are experimental values. The second should be 120 picometer, 121 picometer. But the actual value is neither of this. Instead of that, it is 128 picometer. Okay. I hope you are getting the point here. Now, what we can say, that neither of these two structures known as the Lewis structure are able to determine the overall characteristic of this O3 molecule. Therefore, we introduced a third Lewis structure which is known as resonance hybrid. Okay. And there what we said? We said that since your bond length is intermediate between the second and first. Now what is the meaning of this intermediate? Means it is greater than 121 and less than 148. So it is in between these two, which is equals to 128 picometer. Therefore, we can say that these two bonds are neither single nor double. They are partially double. Means more than single and less than double. I hope this point is clear to you. So I am repeating it all so that you can summarize it. First, we take the O3 molecule, we draw the Lewis structure. Two cases of bonds are possible, single bond and double bond. Now, from the previous experimental data, single bond is 148 and double bond is 121. So, it was found experimentally that neither of this bond is 148 nor is 121. But instead of that, both of these are 128 picometer, which is in between the two values. And hence, we reached at the conclusion that your bond between the oxygens are a partial double bond, and neither it is single nor it is double. And this is the outcome of the resonance, because your electrons are being not localized at one place. Instead, it is moving throughout the oxygen molecule. So you can think it of a trackway for the electrons to move like this, like a current. It is moving from one oxygen onto the other. Now I am not showing the movement of these electrons right now. So I am giving this you as a homework. We will see the electron movement in the next class, where we will do our exercise on it. But for now, you can just look up on the textbook and try to understand that how these electrons are moving through the oxygen molecule. You do it with the help of curve arrows. Okay. So this is the experimental evidence of the resonance, that your single structure is not explaining anything. Now a second question from the previous slides discussion, that why are we getting a greater distance for a single bond and a lesser distance for the double bond? Can you think of it? Why are we getting a smaller value for the single bond and a greater value for the double bond? So just think about it. If you have an answer, well and good. I will tell you in the later on slides, upcoming slides. But you should know this, because we have already discussed this part. Right? Again, I am repeating my question. So why is the single bond longer as compared to the double bond? We have seen the relation between the bond order and your bond length. So what we have seen there? We have seen that bond order is inversely proportional to the bond length. So greater is the bond order, smaller is the bond length. You can see here in the 148 picometer part, if you take the single bond, then it has a bond order of 1. So I am not telling it for this molecule, okay? So do not get confused. It is not for this O3. I am taking a general case. If the oxygen has a single bond, in that case I am saying, okay? Because here you know that O bond is not single, neither double. It is between the two. So again I am repeating it. Since this O bond is single, therefore the bond length is increasing, and here the bond order is increasing, therefore the bond length is decreasing. They have a inverse relation between the two. I hope this is clear to you. Now, here is a question for you. So we will discuss this question in the next class. Explain the structure of CO3 2- in terms of resonance. I am leaving this question on to you. Just try to draw the resonance structure by yourself by moving arrows and all, and I will help you to draw the same in the next class. Okay. Now, moving on to the last part of the canonical structure, which is characteristics of the canonical structure. What are those characteristics? Yes, the double bond will be more stable and shorter in length. It will be more stable, yes. And the longer bond will be the single bond, and it will be less stable. Now, if I talk about the characteristics of the canonical structure, then the first characteristic is that canonical structure have no real existence. Means if you look for the molecule in the canonical form inside your reaction mixture or inside your compound, then you will not see it. If it was there, then you must have gotten 148 picometer and 121 picometer as the bond length. But that was not the case. Means your canonical structure has no real existence. Okay. Second thing, if you see two canonical structures, then in both of them, the position of nuclei will not be changed. Means the atom will be always in their place. Only the electrons will move throughout the molecule. Third thing, two canonical structures are always separated by this double-headed arrow. So these are important and significant point while drawing the resonance structure. In your board exams, it is mandatory to consider this in your answer, or marks are deducted for this. For this is a very small and conventional according to the resonant structure. Now, next and the most important point of all of this, that your resonance hybrid that we have seen and the canonical structure, if you compare their energy, then your resonance hybrid is always in the lower energy state as compared to the canonical structure. So let us try to understand all of these points with the help of the actual O3 molecule that we have seen just now. If you see in this case, you can clearly identify that in the canonical structure 1 and 2, the oxygens are in their same respective position. Only the number of electron is changing. If you take this case, the first canonical structure, then where it is written as 148 picometer, if you see, the number of electrons is 1, 2, 3, 4, 5, 6. Means 3 lone pairs are there on the left hand side oxygen and 2 lone pairs are there on the right hand side oxygen. Whereas on the second resonance structure, if you see, then there are 2 lone pairs and 3 lone pairs on the opposite side. Means the electrons have traveled from left side to the right side. Therefore, we are getting a different kind of structure. Is it clear? Again, I am repeating it, that the position of the oxygen is not being changed from one resonating structure to other or from one canonical structure to other. Only the electron is shifting from one side to the other. And the same is true for the hybrid structure also, that the position of nuclei is fixed. If I ask you that which one is having the highest energy out of these 3 structures, then what would be your answer? Out of 1, 2 and 3, which will have the highest energy? So we've already seen the energy relation between the canonical and the resonance hybrid. So the third one will have the, so I'm talking about the lowest energy. So which one will have the lowest energy? Yes, the third one will have the lowest energy because it is the resonance hybrid. Whereas if you consider the structure 1 and 2, okay, if you consider structure 1 and 2, then they will have higher energy as compared to the hybrid one. Okay, so it's very, very important to remember this point. Okay, if I ask you one more question, that what is the relation between these 1 and 2? Are these structures electronically same? What would be your answer? Are their energy same with respect to each other? If you try to see the molecule as a whole, 1 and 2, are they having the same structure? Okay, so yes, the electrons are being moved from one place to another, but in a way they are same. So I'm not saying that electrons have not been delocalized. Yes, they have delocalized, but now to represent the left hand side oxygen, we have a right hand side oxygen, and to represent the right hand side oxygen, we have a left hand side oxygen. So basically, the electronic energy is being conserved in a way. How do we understand it? Suppose you are standing on a plane. Okay, now you stood up and got up to a table, right? So what will happen? You have moved to a higher ground. Okay, therefore your potential energy will increase, isn't it? Again, I am repeating my example, so it's very important to understand it. So this is not true for every resonance structure. I am talking only about the O3. So again, I am telling it. Suppose you stood up to a table, okay, which is long enough. Now you are standing on a table which is at a higher altitude. Therefore, you will be at a higher potential energy because the value of potential energy increases with height. You know it very well. Okay. Now, if you are walking on the table, there will be no change in the potential energy. Why? Because although you are changing your coordinates on the table, but you are still on the same height. So maybe your kinetic energy will change, but your potential energy will remain same. Okay. Similarly here, although the electrons have moved from one place to another, but electronically the distribution is same, right? Therefore, these two will have the same energy. And such type of resonating structure, such special type of resonating structure where the two resonating structures are almost same, they are named as equivalent resonant structures. Got it? So it's very, very important point. Now I will try to discuss more about it when we will know the actual shape and size and all. But for now, I'm just giving you a very important idea here. Since your structure 1 and 2 are electronically same, therefore they will be called as equivalent structure. So I would suggest you to write it anywhere if you are noting this all down. Okay. So it's very important to make notes of all of this if you are doing it. So meanwhile you are covering the lecture, do it at the same time. Try to make short notes. Later on you can magnify it according to you. Okay, so this will be good enough to prepare for examination. So they are called as equivalent resonating structure and they will have the same energy always. Got it? So this is all about the resonance for now. When we will know more about the structure through the Vesper theory, there I will tell you more about the stability and all. So this is a small introduction for you. Now next is a very important discussion which is known as polarity of bond. So for that, let us take a picture of HF molecule. Okay. So here this diagram is showing the bonded electron cloud. Okay. And if you look at the cloud, you can just think it in a way that the electron cloud of the hydrogen is being attracted towards the fluorine. Why it is attracted? We know the property of electronegativity, that whenever your two atoms are binded and they have different electronegativity, then the more electronegative one will attract the shared pair towards itself. Therefore, the electron cloud will be more on the fluorine as compared to the hydrogen. And as a result of that, a delta negative charge will develop on fluorine, whereas a delta positive charge will develop on hydrogen. Is it clear? So why this thing is happening? So 3 points are important here. They have a different electronegativity due to which the electrons are distributed unequally. More electron cloud is there on fluorine, means the shared pair of electron is more on the fluorine and less on the hydrogen. Now, this electron cloud shift towards the more electronegative atom creates a delta negative charge on fluorine, and due to removal of electron from hydrogen, it has a delta positive charge. As a result of this, you are creating a dipole. Now, what is the meaning of dipole? Dipole, you can think of it in a simple way. It is an entity which is having a positive and a negative charge separated by a distance. Okay, so this is your positive charge hydrogen and this is your negatively charged fluorine, and they are being apart from each other by a small distance, and this whole setup is called as dipole. And a very important property of this dipole is that it is polar in nature. Okay, what is polar basically? So you must have heard this term polar in terms of North Pole and South Pole. So whenever we take two different kind of, I would say, two opposite pictures of each other, then and we keep it with intact with each other, we call them as polar. You can think of the North Pole and South Pole of a magnet, or the North Pole or South Pole of the Earth, or here the positive or negative charge of the HF molecule. Okay. Now, this polarity of bond will keep on increasing if the electronegativity difference between the two atoms is high. Suppose if I take HCl here, then which will have more polarity, the HF bond or the HCl bond? So there is no anomaly in it. You don't have to think about it. There is never anomaly in it. Okay, now there may be a chance that the polarity is more in case of HCl and HF. So I'm leaving this thing to you. Okay, because a second factor is also there which is deciding the polarity, and that factor is distance. So we'll talk about it later. For now, if you want, you can go up to the internet and search for the polarity of HF and HCl. I'm not disclosing it right now, but remember it will depend on two things. First is charge and second is distance. So charge is itself not enough to explain this. But we can think of a different thing, which is OH and NH. You can compare these two. Why I am not comparing HF and HCl? Because if you consider the HF and HCl, then fluorine and chlorine, they are both of different periods. Therefore, the distance or the size will change dramatically, and the distance between the HCl and HF will impact the polarity because they are in the different periods. Whereas in this case, if you consider the hydrogen with oxygen and hydrogen with nitrogen, since oxygen and nitrogen both are in the same period, so we can only choose the electronegativity to define the polarity of the bond. Is it clear? So this is an important point to consider. If you consider HF and HCl, then fluorine and chlorine are from different periods. Therefore, you also have to account for the distance between the hydrogen and chlorine and hydrogen and fluorine. But your nitrogen and oxygen are from the same period, so you have to only think of the electronegativity. That's it. Is it clear? So we have discussed a lot about this. Now we will try to quantify this polarity. How do we quantify it? So we have a special term to quantify this polarity, and that special term is called as dipole moment. Quantifying means giving a measurable value. Now we will talk about this dipole moment. So this is an important discussion relating to the apart from the theoretical part, it is related to the calculative part, right? Okay. Before moving on to that, I am giving you a point of stop here, and you should here try to think about non-polar covalent molecule. So if I ask you that what are the non-polar covalent molecules, then what would be your answer? So you can just write it on your notebook for now, and let me disclose this for you. If you are just guessing it right, well and good. If not, then you should remember it. It's very important. Now, what are the example of non-polar covalent molecules? To understand what is non-polar, first you should know that this whole polarity thing is developing due to the difference in electronegativity. Yes, CO2 is a good one, so that we will discuss later. But now we are taking simple molecules like H2. Okay, so H2 is what? It is homonuclear diatomic, means both of the atoms are same in the molecule, like your H2, where both atoms are hydrogen, O2, both atoms are oxygen, and Cl2, both atoms are chlorine. So all of these will be non-polar because the difference in their electronegativity will be 0. Got it? Similarly in nitrogen and same in the fluorine. And the difference is in electronegativity was the main cause for the development of polarity. Okay. For the case of noble gases, I guess you don't have to worry about the dipole moment because it is existing as a single species. Okay, so in case of bonded structure, you should be worried about it. So you can understand this symmetrical electron distribution from this diagram. See, we have one hydrogen here and one hydrogen here, and the electron cloud is very symmetrical, means it is symmetrically present on the first and on the second hydrogen. Therefore, due to this equal distribution of electron cloud, your hydrogen molecule will be a non-polar one. So what we can say, due to the equal attraction by the two atoms, the shared pair of electron cloud is equally distributed between these two atoms or these two nuclei of hydrogen. Now here is a question for you. Can you think of some examples which are non-polar and they are not homonuclear diatomic molecules? We have already seen one example. I have dictated it. So your molecule should be non-polar and it should not be homonuclear diatomic, means both should not be of the same species. No, NH3 will not be the one. It should be CO2. So this question will only be answered when you are well aware about the shape of the molecule. For now, you are unaware about that. So we will discuss this part when we will talk about the Vesper theory. But for now, you can just check for the CO2 molecule and see that why it is non-polar. Yes, BF3 is also a good example for that. So let us move on to the dipole moment and try to understand this with the help of a formula. So there is nothing difficult to understand it. Simple formulas are there. Just we will go through it quickly. If I define it, it is simply the magnitude of charge and the negative charge and the positive charge distance multiplied with each other. So Q multiplied by R gives you your dipole moment. And this dipole moment is represented by a Greek letter which is mu. So we can write the complete mathematical form. Mu is equals to Q into R. And this is generally represented in terms of dBi units. But how do we know that it is whether in dBi units or not? So you have to simply convert that part if you are getting 1. How we will convert it? There is a simple factor to that. Suppose you are using the SI unit of charge, which is coulomb, and the SI unit of distance, which is meter. You will get your answer in coulomb meter. Now to convert this coulomb meter into dBi, you will use this relation between the two. I will explain you the same with the help of an example. So what is C here? C is the coulomb and M is the meter. So do not confuse it with the centimeter. It is not centimeter. What is this dipole moment doing? We have talked about it. So it is a qualitative measure of the polarity of bond. So more the bond is polar, higher will be its dipole moment. Now, we know that the dipole moment is a vector quantity because we have taken a cross product here of charge and distance. Therefore, it will be a vector quantity and that can be represented as crossed arrow. So here is an example of that. Now, a very important part here, just note it down if you are writing it somewhere, that your dipole moment will be starting from hydrogen and moving on to fluorine because fluorine is having a negative charge and your hydrogen is having a positive charge because fluorine is more electronegative than hydrogen. We have seen it. Okay. But this direction will be opposite in case of physics question. So do not confuse it with the physics part. In chemistry, we take the dipole moment direction from positive to negative. In physics, we take it from negative to positive. So remember, this is very important for you and it will disturb you when you will be attempting question in the exams. Now let us try to understand this dipole moment calculation with the help of a HF molecule. Suppose we have a HF molecule and the charge is considered as 1.602 into 10 to the power minus 19. So remember this part always. You will always take the charge as 1.6 into 10 to the power minus 19. Means you will assume that your hydrogen and fluorine is carrying a unit positive charge, or you can say you will assume that your compound is 100% ionic because it happens in ionic compound that there is a complete transfer of electron. So if HF may be ionic, so this is just imagination to calculate the calculated dipole moment, theoretical dipole moment. How do you calculate it? Hydrogen is less electronegative, fluorine is more. So hydrogen will donate its electron onto the fluorine, right? So that will create a negative charge on fluorine. So what will be the charge? It will be 1.602 into 10 to the power minus 19. Okay. If you are aware about the distance between hydrogen and fluorine, if not, well, no issues. It will be given in the exam. So here I am giving it. It is 0.917 angstrom. Then what will be the dipole moment of the molecule? Very simple. Multiply this 2. You will get your dipole moment as 1.468 into 10 to the power minus 29 coulomb meter. Now I have mentioned it earlier that you have to convert this into dBi, and this is a more good method to represent the dipole moment. How do we convert it? We use this factor instead, which says that 1 di is equals to 3.336 into 10 to the power minus 30 coulomb meter. If you use this factor, you will get your mu as 4.40 di. Okay, so I am leaving this calculation on to you. It's very simple. If 1 di is equals to 3.36 into 10 to the power minus 30 coulomb meter, then 1 coulomb meter is equals to 1 by 3.336 into 10 to the power minus 30. Therefore, for 1.468 into 10 to the power minus 29, you will simply divide this 2. Okay, and hence you will get your dipole moment as 4.40 dBi. Remember, here we are considering that for the calculation of dipole moment, your charge will be equals to the electronic charge on one electron, which is 1.602 into 10 to the power minus 19 coulomb. That means you are assuming a complete transfer of electron resulting in an ionic character, but it is not the actual case. We are just using it to calculate the theoretical dipole moment. Now, what is the use of this theoretical dipole moment? So this is the last thing and the important part. Questions are asked here from JEE and NEET both and on regular basis, and for the other competitive exams also this is important. Now, what is that relation? Suppose if you consider a bond, and we have already told about it, that if you are considering a bond, that bond can never be 100% ionic or 100% covalent. There will be always a percentage character of ionic and covalent in each and every bond that you see. So if you consider the bond of NaCl, there also we have covalent character in the bond. If you consider a covalent bond of say CO, there also we have an ionic character. Now, how do we calculate that ionic character? That is the point. It's very simple. Formula is you should use mu observed by mu calculated into 100 to calculate the percentage ionic character. Now, what are these mu observed and mu calculated? You know that you have calculated your dipole moment through a formula, and you can also observe it experimentally. So you take the experimental value, divide it by the calculated value and multiply it with the 100 to get the percentage ionic character. I hope this clears all about your polarity and all. So we'll discuss more about it in the upcoming classes, but this is the calculative part. Okay, thank you for attending the session. I hope you enjoyed the lecture.